Alright, now we're into part 2 of our waves test review. Page 3, number 11. What is the frequency of a sound wave with a wavelength of 10 meters? Assume the sound wave to be traveling in air at STP. Okay, sound wave traveling in STP. What does that mean? Check your reference tables. Our velocity is 331 meters per second. And that's equal to our equation, lambda times f. Our lambda is 10 meters. And we're looking for f. So 331 is equal to 10f. F is 331 divided by 10, and you get 33.1 hertz. Alright, if you look at number 2, it says refer to the diagram to the right. There is no diagram here. And I even checked my original documents, there isn't even a diagram given, so we're just going to skip this question. Number 13, when observed from Earth, the wavelengths of light emitted by a star are shifted toward the red end of the E&M spectrum, which means high wavelength, low frequency. In terms of the Doppler effect, what does this say about how the star is moving relative to the Earth? How do you know? So a little background information about the electromagnetic spectrum, which we'll cover in the next unit after this test. So there are parts of the E&M spectrum. This is pretty much all about light. And part of it involves the visible light, which is our rainbow colors, Roy G. Biv. Okay? So as we go towards the red end, that means we have this, high wavelength, lower frequency. But as we go towards the violet end, it's the opposite. We have lower wavelength, higher frequency. So let me do that. Let me actually specify here. So what is it saying about the light from the star? It means that we're going towards the red end. That means we're going to see higher wavelength and lower frequency. In relation to the Doppler effect, this means that the star is moving away from the Earth. Because if you think about the Doppler effect in ambulances and fire truck sirens, if it's moving towards you, you're going to have a higher pitched, higher frequency. That's towards the violet end. But if it's moving away from you, then you're going to hear lower pitches, lower frequency, bigger wavelength. So that's towards the red end. Okay. And number 14. So me and Mr. Mach are getting into a heated argument about who has the coolest shoes. I think I do have the coolest shoes compared to him. So in a fit of rage, I get so angry! And I'm yelling at him. Alright. So as I'm walking towards him, the sound waves that I'm emitting is going to have, once again, a higher frequency and a shorter wavelength. Because as I'm walking towards him, moving towards him, higher frequency, higher pitch, shorter wavelength. Okay? So imagine if you have a siren emitting noise. It's going to emit wavelengths while it's moving in this direction. It's going to make it closer, whereas here, as it's moving away, it's going to have longer wavelengths. Because what this moving source is doing, it's pushing on those sound waves closer together, causing it to compress, become shorter wavelengths, and therefore higher frequency, higher pitches. Because that moving source is pushing on its own wavelengths. Okay, oopsies. Okay, 15, we look at a standing wave. So this is what it looks like essentially. How many nodes and antinodes are present in the standing wave shown to the right? So the nodes I'm going to circle here in purple. So these are the parts that don't move. We have 4 of them. The antinodes I'm going to draw lines with in green. So we have 3 of them. 4 nodes, 3 antinodes. Okay, and which harmonic does the standing wave represent? It represents the 3rd harmonic. And how do we know that? We look at the number of antinodes there. 1, 2, and 3. So the number of antinodes always matches the harmonic. You're always also going to have one more node than antinodes. Alright. 16. Referring to the same diagram, how many wavelengths separate two successive antinodes? So I have trouble interpreting this, so I'm just going to take it as how many wavelengths are in two successive antinodes. So here and here. That's one full wavelength here. It's going to keep me. Okay, so that's one full wavelength in two successive antinodes. So 17, you're probably not going to see a problem like this on the test, but it doesn't hurt to know. Okay. So if we think back to trig, that must be the nightmares of many of you. Okay. Looks like a sine wave. How many degrees is that? That's 360 degrees total. Here at point P, it divides that wave in half. So this is 180. And here, at each of these, is 90 degrees each. So 90 degrees to 70 degrees over here. Okay. Let's do a different color. Let's bring back the red. Okay. So what point is 90 degrees out of phase with point P? So out of phase meaning 90 degrees away. Out of phase meaning away. Away from. Okay. So point P is right here. So 90 degrees away means over to here or here. There's nothing in this one on the left, so it has to be here on the right, and that is point B. Okay? What is the phase difference between points A and B? So how far apart in phases are points A and B? Over here and here. So A starts at 0, B is 270 degrees away in phase. And C, are there any points in phase with point P? If so, which point? So in phase meaning, it's kind of like a wavelength. There are two identical points. Okay, so anything that's identical to P is actually D. Okay, 18 is an image to the right showing longitudinal wavefronts approaching a barrier between shallow water, which is here on the left side. Shallow, which is where all the kids go. And the deep side on the right, where all the cool kids go. Just kidding, guys. Okay. So using a straight edge measure and record the distance of one wavelength in shallow water. So I approximated it when I took a ruler, that it was approximately 0.7 centimeters. Okay? So if the speed of the wave triples as it moves into the deep water, what will the wavelength between the successive fronts be in deep water? Alright, so this requires us knowing the relationship here. So if V, the velocity, goes up, the wavelength will also go up in response. So here we're going to show lines that are bigger. They're going to be bigger and longer apart. Okay, so if the speed triples, the wavelength will also triple. So wavelength will then be 2.1 centimeters. Alright, so for part C, we got to use a straight edge and draw 3 wavefronts of the wave in deep water. Okay, let's start here. Approximately 3 of these apart. Another one over here, approximately. And another one over here, approximately. Okay. Just about. And that's it. 19. The diagram to the right represents a transverse wave traveling to the right through a medium. Alright, this is a tricky one to explain and hopefully help you guys understand. Point A represents a particle of the medium. So, first, waves only transport energy. They do not cause the medium to move. They only cause the particles of the medium to vibrate either up or down, back and forth, or diagonally, depending on the kind of wave you have. Alright. So, in general, which of the following represents the direction of motion of particles in the medium? Alright, since we have a transverse wave, the particles are going to vibrate up and down as they move across. As the wave is moving to the right, the particles are going to vibrate up and down in a transverse wave. In which direction will particle A move at the next instant of time? So this is actually the trickiest question here, and I'm going to take a while to explain it, but the answer is B, down. So each second this point A is going to remain still in its spot, and it's only going to vibrate either up or down. So if we keep that same point A, but the wave travels. Alright. So if I show this wave moving to the right, I'm going to draw it over here. So in this next instant, overall A moves downward. So this is originally A, it's going to move downward on this next point. If I draw another wave with another color, let's do green. It's ugly. Someone's dissing my work. Okay, so once again, it looks like it's moving further down. So if you focus on where these waves intersect with this blue line, you're going to notice it goes further and further down overall on the wave. So focus on where these points intersect, these waves intersect with this blue line, and notice that at this point, point A, it's moving further and further down. Okay. Okay, the final part. The last few questions. The final stretch, guys. Number 20. The Doppler effect tells us that as waves move toward an observer, the frequency of the wave, so the frequency relates to what? The pitch. Oops. Okay. So this is the pitch of the sound. So, as it's moving toward, it should be increasing. The Doppler effect tells us as the wave moves toward an observer, the wavelength, on the other hand, decreases. So if frequency increases, the wavelength should decrease as a result. They get shorter and shorter, shorter together. The Doppler effect tells us as the waves move toward an observer, the speed of the wave as compared to when this wave is stationary with respect to the observer, this one's actually going to stay the same. Because if you have frequency increasing, wavelength decreasing, these two changes acting simultaneously will keep the speed the same. If you look at our equation here, if you increase one of them, speed is going to go up. If you decrease one of them, speed will also go down. But if you increase one of them and decrease the other one in equal fashion, then the speed will still stay the same. Okay? 23. Two pulses A and B travel toward each other along the same rope as shown to the right. When the centers of the two pulses meet at point X, the amplitude at the center of the resultant pulse will be. Okay, so what type of interference is this? This is destructive interference. So what we're going to do, we're going to take their amplitudes and get a smaller one. Destructive. So here we have +2 and a -1, this becomes +1. So this new one will end up looking like this. Okay. And that is it, actually. So these aren't exactly Regents-style questions that you'll probably encounter on the test, but nevertheless, they still cover the same ideas, same content you'll see. Hope this has been helpful, and don't forget to make sure you have done the actual review questions on your own and use this video to check your answers, and make sure you have it all completed for submission so that I can give you guys a homework grade, and good luck.